Bien, muy buenas tardes. Tengan todos ustedes muy bienvenidas, bienvenidos a esta conferencia del doctor Stojadinović, quien vino a México para asistir a una reunión sobre resiliencia que organizan otras escuelas, otras instituciones, y amablemente pues ha dado parte de su tiempo para estar el día de hoy con nosotros y hacer esta presentación sobre una evolución del diseño por desempeño a un diseño basado en resiliencia, y nos va a comentar los trabajos de investigación que se realizan en su instituto en Suiza alrededor de este tema. El doctor Stojadinović recibió sus títulos de posgrado en la Universidad de California en Berkeley, habiéndose graduado, titulándose inicialmente en Serbia. Él es de origen serbio. Posteriormente fue profesor en la Universidad de Michigan, regresó a la Universidad de California en Berkeley y de ahí emigró a Suiza, en donde actualmente es profesor con la cátedra de Ingeniería Sísmica y Dinámica Estructural en la Escuela ETH de Suiza, una de las escuelas más prestigiadas en general en muchos temas, particularmente en el asunto de las ingenierías. Entonces, un instituto de mucho prestigio. Y bueno, como mencioné, ha hecho investigación en temas de diseño por desempeño, resiliencia. Su tesis originalmente fue comportamiento de estructuras metálicas. Ha trabajado en diversos temas relacionados con la ingeniería sísmica y actualmente está haciendo una estancia en un centro que tienen conjuntamente con la Universidad de Singapur, el ETH, sobre igualmente temas de resiliencia. Entonces está pasando parte de su tiempo en Singapur. Yo supongo que él ya nos explicará con más detalle. Entonces para mí es un privilegio recibirlo, es un muy buen amigo, siempre ha sido muy solidario con el instituto y nos da mucho gusto que se haya dado el tiempo para estar con nosotros. Muchas gracias a todos ustedes y thank you very much, and the floor is yours.
Yeah, thank you, Sergio. Thank you, Professor Alcocer, and thank you all for coming. Is the microphone working? I hope it is. Yeah, I guess it is. So it is a pleasure to be here, of course, and especially in the sense that being in Professor Emilio Rosenblut's room, he is one of the greats of civil engineering and earthquake engineering and probabilistic earthquake engineering, and it's really a good thing that we continue that tradition and remember that, because some of the things that I'm also going to talk about have to do with what he has started some long time ago. So what I want to do is to talk about this evolution of the way we design and how we got a little bit into performance-based design, but how we're going to move, how the profession, all of us together, are going to move hopefully towards the next level, which I'm going to hypothesize here is going to be resilience-based seismic design. So let's start. I mean, in some sense, I'm reasonably sure that everybody in this room has seen a picture of this quality, and perhaps with these same buildings that are supposed to state that a building has more than one damage state. In fact, it has a continuum of damage states. And the way that we embraced performance-based design that started to happen in the early 90s, that's 1995 is the publication year of the Fundamental Vision 2000 report, where Professor Bertero was one of the main drivers of that. This was the initiation of a design philosophy that is not focused only on collapsed limit state, but has to take into account all of them. And it is also a design philosophy that's supposed to be technology neutral, meaning that we're not going to do anything specially so for concrete, steel, wood, or any other type of seismic response modification, but we're going to design a unified methodology for design that's going to take care of damage in its continuum and reflect on what that means in terms of the people who die, casualty, get injured, in terms of the direct and indirect losses and the downtime of the facilities that happens after an earthquake, depending on the amount of damage that we have seen. And this Vision 2000 format of multiple performance objectives associated with a hazard level, frequent, expected, design level, or rare, with the performance objectives that are here only 4 of them in terms of operational, medium life safety, and collapse prevention, has taken hold in much of the prototypical performance-based design provisions, and the ones that are now being implemented, perhaps there are one limit state to fewer and one hazard level fewer, but this is how things have gone in the past. And we are in the situation now that when we design, we look still at the demand and capacity comparison. We take input in terms of limit states, in terms of hazard. We use engineering demand parameters. These are drifts or forces to evaluate the structure and figure out if it's good or not, and then iterate also in the design process. And PEER, the Pacific Earthquake Engineering Center, where I happened to work in the early 2000s when the center was going strong, developed this performance-based earthquake engineering framework that has to do with dividing the problem of computing the total probability of a loss into several stages using the total probability theorem. And the first one is, of course, the hazard. Then we have to do some structural analysis, figure out what is the consequential amount of drift or force in the structure. Based on that and some test experience, or perhaps really good models, we do damage analysis and assess the damage state of the structure. And when we are done with that, we can figure out how much it costs or if anybody is going to die, if there's going to be a collapse or not. And so this kind of a 4-stage process has also been accepted in our profession and is entering ASC7, the modern codes, the FEMA P58, entire system of manuals has been built around this idea. And the more modern retrofit codes like the ASC 41 or the Swiss 269 are also looking into this idea and accepting it. And why is that so? Because it works. And here, I mean, it's easy to choose examples in Mexico City because there are earthquakes and big ones. And comparing 1985 and 2017 one, there were collapses in both, but many, many more in 1985. So many more people died. And the changes in the code that Professor Alcocer also wrote about, and you know in the evolution of the code what it meant in terms of the spectrum shape, in terms of the requirement for thicknesses and strengths, have shown to work. They don't prevent collapses completely. Probabilistically, that's a little hard to do given the uncertainties we have, but make them smaller, they may fewer, so we don't have as many casualties. Now, the economic damage is a different story. It's a very different story, and here this is a huge city, so it may not have been felt as much as in Christchurch. And this is, of course, the New Zealand 2011-12 series, where they were basically left without their central business district in their downtown. And that meant that people couldn't go there to work, offices, small businesses, and it was cordoned off for, I think, 2 years. And in the meantime, they decided to make a whole new urban plan for that, and so further delaying the reassumption of business in that area. And this kind of not only direct losses in terms of the rebuilding or repairing of the structures that they want to do, but indirect losses in terms of just economic numbers, in terms of later on people emigrating out of New Zealand or out of that part of New Zealand to find work, are also to be accounted for. And what performance-based engineering does is it enables us to consider multiple limit states, the ones that have to do with the reduction of direct damage and with enabling repairs. This repairability is becoming quite an interesting option. In many talks recently that I've seen, Professor Ken Elwood gave a keynote lecture at the American National Conference for Earthquake Engineering last year. With the title, in the title there was something about repairability, so go take a look at that. That's on ERI's website. That was an interesting talk. So let's see if I skipped. No. But the result of this effort is of this FEMA P58 framework, which extends in some sense or elaborates on the peer framework and lets us figure out how things rank in terms of the casualty risk, in terms of the risk of it being black, green, yellow, or red, in terms of the cost of the repairs, cost of the initial build, the time to repair, and towards the end is also carbon. That's new. But there is this comparison of different structures. As you go from the bottom, these are the unretrofitted, old, non-ductile structures, lots of casualties, probably going to be tagged red, long repair times. They're cheap, but they cost a lot to repair. And you go up towards seismically isolated structures with the usual conclusion. So this framework is quite interesting, but the recovery of the businesses, the recovery of the life of that community, even simply the evacuation and the return of the population are not easily described only in terms of repairs of individual buildings. They have to do with their function. So the notion of functional recovery is higher, bigger than repairability. It is not only restoring the structural integrity of the building, but also the lights, the air conditioning, the internet, the water, the transport to the building, everything that makes this complex building work. I can see that it's easier to do so for an individual house, but even today, individual houses are not as simple as before, and especially when it comes to office buildings or schools. So the functional recovery becomes a new dimension in terms of seismic performance. And there is a recent document by the American ERI that advocates introduction of functional recovery into the process. And what I'm going to start talking about now is something newer, is this red block. It is the functional recovery, or the FREC framework, that was proposed by Vesna Terzic, and also a very kind of a little bit later, but in parallel, the work of ATC 138 committee, a few people there. Essentially, they start with a performance-based framework, and they look at damage. They conduct damage analysis, and then they move on to figuring out how to restore functionality. What does it take to fix the doors, elevators, air conditions, power, water, and everything else the building has in terms of the relation between these functional limit states and structural damage states. To remind you, the way that the steel fractures were discovered after the Northeast earthquake was when in one simple office building, I think 6-7 stories tall, they couldn't get the elevators to work. On the outside, the building looked okay, a few broken windows inside, nothing major. They just couldn't get the elevators to work. Then they simply measured the inclination of the elevator rail and found that it was like 2% off. 2 degrees something off, to how many radian, I don't know, but nevertheless. And then they looked why the entire building was tilting. They opened up one of the connections and saw the one that was the picture that we see all with a broken column. That building basically rose the alarm. And the way it was discovered is because it functionally couldn't get back to where it needs to be. And so once you figure out what needs to be done with the function, you can then plan the recovery effort through the mobilization phase, starting of the work, designing, permitting, getting the resources, contracting this out, and the repair model. And then you can get the functional recovery estimates. And so the way that it seems that things are going to go very shortly with the publication of ATC 138 document or the Vesna's peer report, for example, 2021/6. That's easy to download. her papers also, but they are all listed there. I can see that we're going to divide a little bit the peer methodology, keep the damage on the left and the loss analysis on the right, and add this recovery analysis in the middle, meaning that we are now going to be able to much more accurately compute the downtime and the direct cost, definitely, but the downtime also in terms of the effect that an earthquake had on a building. Unfortunately, there is one thing. Recovering the building's function, recovering the building's power, water, transport access, communication, needs the rest of the infrastructure to be recovered. It cannot be, it doesn't stand alone. Some hospitals have powerful enough generators and big tanks to sustain themselves for a few days. And water also. But that's it. So we are not talking about long survivability off the grid. So we need to have recovery of other structures, and that now has to do with regional risk exposure, all of them together. We have to have recovery of the technical side of the infrastructure systems. And finally, people need to be able to come back into those buildings. They need to want to come back into those buildings. First, feel safe. Example from Turkey. Seismically isolated hospital, for some reason, we can discuss why, probably, had quite a bit of non-structural damage on the first floor. Basically, ceilings, the light ceilings fell down. The doctors wouldn't go in. The patients wouldn't go in, even though it's a seismically isolated hospital. Cannot be better. So there is the psychological, and also there is the economic and all the other things that build this society. So all these are heavily interdependent when you start looking at the region and identify the houses and identify the power lines and then try to group them somehow and see how those networks work. And so this is interdependencies are very difficult to untangle, but here is an example. So when you have casualties and injuries, that overloads the emergency services and hospitals, and housing damage presents then demands for the temporary housing, and you want to start repairing. That is a lot of people and bricks and all that needs to be delivered. When there is no housing on the other end, people are not there, and the power system and the water system do not have as much demand as before, so it may not be all that bad. However, infrastructure is also damaged, and we don't know if the available capacity will satisfy the reduced demand or not. And these are instabilities in the entire system that make people uncomfortable, and they may make a decision to leave, which, at least from the data from Turkey, that region had about 15 million people. 3 million left. They're not in their houses anymore. It is estimated that maybe 1 million in intense, 2 million are somewhere else in Turkey. So this is a shift that may be permanent if the children of those people start going to these other schools. If they find jobs somewhere else, they're not coming back. So this is a complicated problem. And how do we technically look at this? We can start estimating the hazard, the exposure of a region. We can look at the regional hazard or the intensity maps for an earthquake that this region may see. Then, looking at multiple buildings there, we can identify the classes that they belong to, and within those classes, the vulnerabilities that they have. We can also look at the occupancy and the functions that the buildings have right now to assess the damage. Then, when it starts with damage, we can see how much it takes to repair that, what are the resources, how much material and manpower and machines do we need. And then from the functional recoverability side, we now have a pretty good handle with those frameworks, the FREC and ATC 138, on what it takes to recover the internal functions of a building once its structural stability is there. And then only then can we talk about the restart of functions and the reoccupation of those buildings. So it's a very long list of things that need to be done, and especially long when one considers that now you have to know this: intensity of the ground motion, vulnerability of the structure, occupancy, current function, damage state, repair of that, recovery of function, and reintroduction of people, not for one building, for let's say 50,000. Here in Mexico City, maybe 1 million. And I mean, how do you do this? You have to do it statistically. You have to, right now, it may be possible with bigger than big data that we have today to capture this individually, if people were ready also to surrender quite a bit of their privacy in terms of location and in terms of the quality of the building that they live in, and so on and so forth. But now we can do it statistically, and that's probably the best we can do. And with the FREG framework, we can recover, we can see how to recover individual buildings, and typically we would come up with this kind of a flow chart as to what happens when the repair starts. First you do the structural systems and the vertical systems like the stairs and the elevators, and once you enable the people to go up in the building and bring doors and windows, for example, then you start repairing partition walls, pipes, HVAC, and all this other thing. So there is a sequence to how things go. And this is now to be repeated everywhere in the region for every one of those buildings. And what you get for a single building is something like this. This is an example of a 42-story tall building. That comes from other studies in LA, but as you go up, you see the Gantt charts. So you see how some pieces of work start. The blue are structural repairs, and the other ones are non-structural repairs. And you see the delays as you go up the building. And with limited resources, if you do not have, for example, enough people, then there will be further delays, and you can then plot and chart these kinds of resilience curves, the swoosh-like curves that have a drop in functionality, this red region of just preparing to do repairs. For a 42-story building, you're not going to run in and do it right away. You have to plan, and then start gradually going floor by floor up the building and repairing things. And so this is what that framework gives us. But regionally, in terms of infrastructure, we need similar frameworks too. And there are a few, and the one that I'm going to tell you about is this iRecodes framework that my students have developed over time, that we're also now working on in Singapore too. There are others. INCORE is another one. This is the Resilience Center funded by the American NIST, the National Institute of Standards in Colorado State. John Vanderlyn is leading it. They have a very nice framework. Several other researchers, like Professor Cimilaro from Torino, has a nice framework of his own that started when he was in Buffalo, a student, way back when, with Professor Reinhold and Bruno. But the idea is that we want to be able to simulate the operation of the infrastructure systems as it is being vulnerable and damaged and as it recovers. So we model the individual components of each infrastructure system. We lump them a little bit together into localities, so we don't have to analyze every pipe, but some connections we do, some connections we do analyze, and then look at the supply and demand of those components. Why is this important? It is very difficult to exactly chart out how an infrastructure system is going to work in the damaged state, where the water may come from or the power may come from in a multiply connected building. Singly connected buildings, okay. But in that sense, looking at the supply and demand, what does this water pump need to operate? It needs water to pump and power to work. So if it doesn't have power, it may be in super good state, no damage whatsoever, has all the water coming into it, it still cannot work. So these kinds of interdependencies we can capture by listing the multiple supplies and multiple demands that a component needs. So a component has some damage, has some repair scheduling, and during that repair scheduling, we look at the list of demand supplies that it needs, power, water, communication, and whatever it produces, something that that component produces for the infrastructure system, and then balance the entire infrastructure system using this idea of flows through the system. And so this helps us capture interdependencies very, very well. Other frameworks also do it. They often use optimization. You will see we use optimization too, because in this IRECODES framework, we predetermined the sequence of component repair. For example, biggest pump first. Or we also predetermined what the next repair is going to be, and also how to distribute the resources within the region. You can direct the resources to the hospital deliberately, for example. When you have an optimization module like this thing down to your right, then you can put in some minimization criteria and optimize across the system, which takes some time in the computer, but fortunately we can now run a lot of those simulations on parallel computers quickly. So with that, we can look at the region. This is a hypothetical one, a small one, because we wanted to debug the system first, and run an analysis. Here is an earthquake analysis, and the recovery process you see. There is a service level before the event where the infrastructure was running with some supply margin. The blue line is above the black line. And then when the earthquake happened, there is a sudden drop, and then as the repairs happen, you see this stair-like line that signifies that one component is repaired, another one, and there is this difference between the supply and demand. The red line is the demand for that service from the housing that was also damaged and is also recovered. So the difference is what we need, what is the lack of resilience of that system. And this gray area on the bottom is caused by interdependencies. It is this additional loss of resilience that happens. And so, okay, so we can capture that with this IRECODES framework, and it works now quite well. There is a Python version that can run on a parallel machine. We can do many analyses of the same region for a random fault and random vulnerability of components, and even some randomness in how they recover. So it is possible to probabilistically characterize the technical side of the system. But the technical side of the system is not the whole thing. When we recover structural safety, when we even recover function of a building or of a part of an infrastructure system, it is up to the people to start using it again. And the people may not feel safe. The people may not be there. The people may not be ready. In Turkey, for example, the day after the earthquake, the waterworks that has about 1,500 people working there had only 200 repair people show up. The rest, some were dead, but many were busy with their families who didn't have a roof over their head at that time. So even though you're ready to go, you cannot, because the people are not back. And how do you capture this? And we are engineers, and we can do all the numbers that you all know, and maybe even more. But this doesn't help us understand the behavior of the people who are users of our system. And this is a big problem. And a large field of resilience studies that started after Hurricane Katrina has been very focused on this psychological and societal resilience of an individual and resilience of groups of people. And they do a lot of work through indicators. They survey people before and after. They have this idea of social capital, connectivity, bonding, bridging, linking among people that helps them survive a disaster. And we tried several of these approaches, and the one that we kind of sort of think that may work is the capabilities approach. It comes from an economist, Sen, Eritrea Sen, and just Wikipedia this capability approach, and you'll see that. And also Professor Nussbaum, Martha Nussbaum from Holland, she contributed quite a bit also. But it has to do with what a person wants to do. A person wants a good life. That's on the right side. And well-being and education. But to do that, one needs some conversion factors. One needs to have the personality in the community to realize education and hospitals. And that's the societal side. The technical side is the structural safety of the hospital, the availability of water and power and communication there. And so there is this link. The curved arrows show how the capability set will provide more resources for recovery of a community, and therefore the electricity and power and all this is going to be improved, coming back with more conversion factors, enabling more capabilities, more people being able to realize their desires, and so on. And that would be a recovery that kind of circles in this cycle and helps the system build up, and also integrates from a person to a group. So this is still being worked on. Lawrence, the doctoral student in Singapore, at ETH in Singapore, is doing this. But this is something that also Professor Gardoni looked at with Colin Murphy, another professor from Illinois, some 10 years ago. But they stopped at just the damage, at the damage state. But we kind of try to push it towards recovery. And the reason why it's important is because we are dealing with a socio-technical system. It's a system that has the technical part, the bottom part, and that we handle. And the top part, the societal part, and in this middle, we hope to insert this capability approach with resources, conversion factors, and a capability set that enables people to do things. And we will see how it will go. But the socio-technical aspect of recovery and resilience is something that I think we need as a group of engineers to work on very hard, because the technical part, I feel we are not very far from being done, at least conceptually, of how to evaluate it. And this would be a good extension. At least that's what I'm going to try to do next. But to come back to the technical part, here is an approach that we tried, and it does work, of how to do regional recovery simulations, regional resilience simulations. And this is a combination of this FREC framework, N times for every typical building in the region, and the IRECODES framework that does infrastructure recovery. And so conceptually, you start with every building, you get their damage states, you also do that for infrastructure systems, and then once you have building level functional recovery requirements, you do an infrastructure system analysis and see how far off that is and how much delay you have. And do that and do a resilience quantification at the first time step, then repeat the next time step, the next time step, the next time step, as those Gantt charts grow and recover function, buildings recover function, infrastructure recover function, and eventually the entire region recovers function. So here is a picture of how it works. In downtown San Francisco, we picked about 700 buildings for a hypothetical 1900s, not really a weaker earthquake, but a likely one. And the graphs above show you the recovery of the function in 3-story, 13-story, and 42-story buildings. And those are not hand-drawn swoosh curves, but generated stepwise curves that show how repair progresses. And you see the blue one has a lot of steps because that is the 42-story building that needs 42 stories, 42 steps to recover. The bottom graph is also interesting. It shows when there is a shortage of concrete workers, people who do forms and pour concrete. And depending on the dynamics of the recovery in the region, you may or may not have enough. And this is going to slow you down. Or if you can provide more people, cost you more, because at some points in time, you do not need many concrete workers. So this gives you a way of dynamically scheduling regionally the work. So if you go back to what we did with the peer methodology and that framework that had 4 steps and then the recovery, we can do the same on the regional level. We can say, okay, we do the hazard regionally, we do vulnerability regionally, we do recovery regionally with this FREC and IRE codes combination, and we quantify resilience. So the idea is, what I want to show you by this slide is that it was, in the meantime, a conceptual step forward from performance-based design for individual buildings with some assumptions, quite a lot of integration, quite a lot of computation. We moved towards regional assessment of all of them together. And not only that, since we can now track over time how recovery goes, we can reconstruct those resilience curves and quantify resilience. So this is a key part, the fundamental step in going from performance-based design for single structures to recovery-based design, resilience-based design for a region. So if everything goes well, we may be able to do a Vision 2000 format, but for resilience, to have some hazard levels and a bunch of performance level objectives, operational or collapsed, communities collapsed when people moved out, and do that for all the infrastructure systems and systems, healthcare system, school system, small businesses in the region. And each one of the blocks we can now quantify how resilient or not resilient it is, how quickly it recovers and how slowly it recovers. And so in the IRE codes, here is how we do this. We look at the supply for a certain resource, say power, and we look at the demand as it changes. Both change in an earthquake. Both drop initially. Here the demand happens to recover quicker, has a smaller drop and recovers quicker than supply. And the area in between, well, I'll get to the area in between. The green line is the overall consumption of that resource. So even though you have some supply and you have some demand, your consumption is lagging yet because there is no connectivity in this particular illustration. So when we look at the resilience metric, which is this area between the system demand and what the system consumes, this is what we term lack of resilience. This is the area that originally in MCR, in that paper that's whose first author is Michel Bruno, but it is the entire center who took part in formulating, was all the way to the top of the graph, looking only at the supply. Here we note that the demand changes too, the consumption changes too, and we see that lack of resilience is the difference between what people would want to spend, use, consume, and what they really consume, and how that recovers. There are other measures that characterize the swooshiness of this curve. The first derivative, when it drops, the first derivative when it recovers, the robustness is some kind of a minimum drop, the smallest drop that it has overall to the minimum point. The area this time of average performance loss is a normalized area, and so on. And there are even proposals for a multiplicative index. But what I want to focus on is this duration of recovery. Duration of recovery is just the time distance from the event until you come back. And this is something that the NIST, the American Institute for Standards, has taken on as the key measure. It's a simple measure. But they published a document 2 years ago, this NIST 1190, which again you can download easily. And there the duration to X% recovery is the key metric. So what X is varies, and the duration, of course, then varies depending on this resilience curve, on the swoosh curve. And then they said, okay, what is acceptable? What could be acceptable? This example stems from San Francisco downtown being hit by a 1906-like earthquake. So it's not general, but the format is general. So they say, okay, critical facilities are building, transportation system, water, communications, and they want 90% recovery in short term, which is a few days. And the x's are where they think the systems are now. So there is quite a large time gap between what's desired, the green block, the green squares and the blue squares. And then they go down into emergency housing, a little bit longer to recover, normal housing, and then finally community recovery. So there is a little bit of a shift in these graphs. And generally, the format of the acceptance criteria has to do with functional recovery categories that are defined in this document, and the frequency of an event. The frequent earthquake, design level, expected earthquake, and maximum considered earthquake. And you see the blocks are how many days or weeks or months, hours or days are needed to recover. So before we were thinking of the performance objectives, expected earthquake, immediate occupancy. Now we think expected earthquake for functional recovery A, hours or less for full functional recovery, or 90% functional recovery, depending on the particular region, particular code, particular hazard. So this is the format of those acceptance criteria. And over time, I have been pushing students, and they have been doing a really good job to match exactly this need with the recovery in terms of this area between the demand and the consumption. We can note when this 90% or X% point comes in. And also in this second from the left graph for electric power, we can also capture cascades and periods when things are really bad and then they recover and then they get bad again, and capture those also, and compute where the system is now, those red outlined blue squares set where the system is now, and also see how far it is from the desired state. So these are all building blocks of performance resilience-based design in this Vision 2000 format, where now the squares for every infrastructure system would be explained in this NIST 1190 format. So in that sense, we can do a lot. We can do one more thing. We can see how to affect resilience of a region. Just to put it very simply, this is a separate presentation altogether. We can increase robustness. And that alone will make the drop smaller and the recovery faster. Or we can increase the number of recovery resources, the amount of recovery resources. And here, this blue line and the dispersion around it shows you the recovery time with a few resources on the left and many resources on the right. And you see there is a saturation at some point. Adding more resources doesn't reduce your recovery time very much. So that's kind of like your sweet spot. But if you are low on resources, your recovery time is going to be long and your uncertainty is going to be high. So bad and then double bad. And having these tools, we can then say, okay, fine. We can put together a design flow chart for resilience-based design. And it is the same design flowchart that we always use. We set some objectives. When you design a beam, you don't want deflection to be very large, and you want to carry the load. For performance-based design, there are a few objectives. For resilience-based design, there are many more. We have perhaps a trial design if you're designing something new, or we can evaluate an existing state. And we can ask yourself, are these resilience objectives attained with this particular situation? And if not, we can improve. We can set measures as to how to improve it. Right now, this is why I think we are very near being able to do resilience-based design. Here are two opportunities. Many of you may have heard that Jakarta is sinking. This is the capital of Indonesia. And first of all, it's sinking anyway because it's too heavy. The soil is simply bad. And then the water level is rising overall because of climate change. So the government decided to move many government functions into a new capital. And this Nusantara is going to be on Borneo, on a whole different island, and it's an empty field. And you can see they started digging a little bit. And this is the at least the first phase of this future city. Doing resilience for this is just right, because you start at the very beginning, you can test alternatives, you can talk with urban planners, you can do a lot to make it more resilient. But this probably will not happen again in our lifetimes. Much more common is local change. This is a small, part of the map of Singapore, and down here is the center. This is where all the tall buildings are. This is the marina and this iconic images. And here is the port, and this over here is the new development. And last year when I was there, they were kind of like halfway up to the top of these buildings, but you see there are, 40 or so story buildings, a bunch of swimming pools. This is a new town. So every one of these buildings has probably about 5,000 to 6,000 people, 9 of them, 50,000 people. This is a pretty nice neighborhood. And you can do a resilience analysis of that neighborhood, figure out how much power, water, communication, redundancies, transportation, and all that it needs. How far is it from the hospital? Are these 50,000 people going to overload the nearby university hospital or not, and so on. You can also look at how this addition will affect all the other neighborhoods that are also sourcing from the same source of resources. Schools, for example. How many new schools do you need if you are going to do this? And so this is something that I think is much closer to actually coming about. And so we have to be able to do this resilience assessment and then collaborate with urban planners and perhaps policymakers, also local governments, to direct their efforts in redeveloping of urban areas towards making them more resilient. And we know how, because we have this design, this framework that we can do it with. But there are still many challenges, and we are too focused on technical systems, and hopefully we'll get more societal aspects in there, and also finally the cost-benefit analysis. This may be the most difficult one because it has to do with the economy, and there are colleagues of mine at the FRS who are trying to even tackle that using the input-output table approach. You can Google that, IO table, input-output table approach. The colleagues in Colorado Boulder at the NIST Center there are using the computable general equilibrium of the economy of a region as another way to do this. But those are still quite in their infant stages, and as are the societal aspects, of course. But I think the biggest problem is for us is just change. We are doing this design having in mind a 50-year horizon, a 100-year horizon in terms of hazard, but also in terms of people living there. This neighborhood in Singapore is going to be there for 50 years for sure, if not longer. But in the meantime, we'll have climate change there, everywhere. We'll have technology change. What is going to happen in Singapore imminently is electric vehicles. In 2030, they will ban import of anything that burns carbon. So that the shift of about 1 million vehicles to electric will happen in the next 10, 15 years. That means chargers everywhere, a lot of more power, electric power. The society will change. People will like to do this or that. During COVID, we somehow learned to like to stay at home. And it's difficult to get people back into the office. It's difficult to get people back into the restaurants, which is good or bad, but it is a societal change that affects how our systems work. And if we design today, there is really no way to predict this. So we can say, okay, let's make our systems resilient to those changes. Fine, we can try, but how are we going to know if this glasses that Apple released the other week and Facebook Meta are going to make us stay at home even more or not? We don't know. So we've got to kind of sort of do something clever. I don't know what that is. So with that, those are the challenges, but I hope I convinced you that there is a path forward from performance-based design to resilience-based design. And I outlined a few steps. Again, I used what my group is doing, what my students are doing, because that's what I know best. There are other people who do this, and certainly as a community of engineers will come around to something of this format. And definitely, if nothing else comes to your hands after this, the NIST 1190 report is a really good place to start. And with that, I'll just thank Dr. Nikola Blagojević, who did a lot of work on IRE codes with several master students, and Mr. Hamed Hafeznia and Mr. Lawrence Seng, who are now my students in Singapore, with who I work with on these optimization problems and also on this capabilities approach. And so with that, I end. Thank you very much. Thank you.
Thank you very much. And primero tengo que agradecer a los capítulos del ERI, de la Sociedad Mexicana de Ingeniería Estructural y Ingeniería Sísmica, que han coorganizado este encuentro, así es que muchas gracias. Y también mencionar, there are 110 people connected online.
Oh, great, thank you.
95 in YouTube and 15 in Facebook. And they have been following your talk. So there are two questions online that I want to read to you. The first one reads like this. De Juan Manuel Sandoval. Urban planning regulations should include an infrastructure system as part of the perspective of the city. That's one question. And the other one is from Eduardo Ismael. How can we include the quality of construction procedures and materials into the community resilience framework?
Yes, okay. So the second one is a little bit easier. And we can do that by diligently analyzing the vulnerabilities of the existing structures. This we can do modeling, testing. For example, the test that I saw today were retrofits of an existing building with shear critical columns. The shear critical column building probably has not much in terms of studying its vulnerability. It's going to go down very quickly. But the retrofitted building, that would be the next step of your research to see how that whole building is now going to behave, how vulnerable is it going to be with those cages around the columns, for example. Cyprian is studying the vulnerability of indigenous housing, those non-constructed housing. We have to make an effort to capture the things that are very difficult to model. And the way that I see this moving forward is by experimentation. You have a lab, we have a lab, let's do tests. Yes, it will cost money. We have to convince the sponsors that this is the weak spot in our knowledge, and I agree it is. And so the second question was to do with infrastructure systems on the regional level. So design of infrastructure systems is an area that only a few civil engineers get into. Many, many more become building or bridge engineers. But some of our colleagues do waterworks, do go transportation systems. Some of our mechanical engineering or electrical engineering colleagues build the power system. And the communication guys are a whole different group of engineers. Those are the people, typically electrical, mechanical guys, who are not as aware of the risks as we are. They are very aware of the wear and tear, the use, the maintenance issues, the repairability issues. They know this very, very well. Talking to them about a flood, an earthquake, is not productive. In their lives, they may not have seen any, and perhaps they don't expect to, or one. And that was an emergency. They somehow survived it and don't want to think about it. So it is, I think, the way for us to go is to approach them nicely and to suggest that on top of their maintenance scheduling, perhaps using a framework like this FREC, we can study heavier damage that is very rare, but include it in those schedules. And there is a huge opportunity there when they maintain or build out a small portion of the system, but definitely maintain the existing one. They can, in the same time, strengthen it. In Los Angeles, there was a big campaign led by Craig Davis, he worked for their waterworks, on changing the brittle iron pipe with ductile plastic something, I don't know exactly the name right now, but a much more deformable pipe, much more forgiving pipe that is likely to resist motion, ground motion during an earthquake. And so this is an opportunity with infrastructure. While you maintain, you improve robustness, and talk to these people. Many of them are not aware of the hazards that we work with.
Thank you very much. ¿Alguna pregunta aquí en el salón? Doctor, por favor.
Thank you very much for your presentation. I very much inspired by the work of Gray and water systems. We are introducing in our research in this recovery time. We have two parameters. One is, of course, functionality. The other one is operability.
Yes.
And I wonder, have you thought how to introduce this new variable into your concept of resilience of communities? Because operability, perhaps for a water system, for an electric network, even for a communication network, it could be something more understandable. But when you go to buildings, that creates some problem. Yeah, we've been working in resilience-based design, where we are not introducing in the design the definition of local displacements in the structure, but also the intensity of them. The intensity, because that will define really the recovery time. But for me, it's difficult to imagine if I got a crowd, a group of people repairing a certain room of a building, whether when it would be operability, when it would be functionality. That how you could introduce that.
So this is I think a very important advance that is done by ATC 138 and also separately, but very similar, Vesna Terzic with this FREC framework. It is a synergy of structural repairs followed by a set of other repairs that return the function to the building. Elevators, stairs, power, water, air conditioning, communication, and I forget what else. How did she do this? She interviewed, I don't know, I think 10, 15 engineers who were repairing taller buildings in Los Angeles after the Northridge earthquake. So the data is a little bit old, as are the engineers. But we haven't had another earthquake in the meantime. So this is as good as it gets. And through interviewing them, she got a little bit of an idea as to this. So what is the link between restoring structural safety? What is the link between restoring power on this floor, just functionality, and actually making this operable, making this useful? And so in the model that she has, a floor of a building becomes usable by people. They can walk in and turn their computers on, for example, if it's an office, when all of the infrastructure is working there. There is power, there is water, there is toilets, there is kitchens, there is air conditioning, there is internet, there is all this. And so this means that you could, in a very tall building, have a wave of occupancy starting from the bottom. Now, I think that this is very specific to the operator of the building and the function that it houses. If you are dealing with an office building where the offices are separated horizontally, doctors' offices, lawyers' offices, they don't have vertical connectivity, then perhaps you can do it. If it's a more complicated operation, then you need both. And this is where I think we would get into custom level solutions. So the way that this is formalized is through fault trees. It is they use the fault tree approach. It is the same thing that nuclear people do and airplane safety people do. Maybe that's too detailed. Maybe something more fuzzy can be used. But this is, I think, a place where we will need to invest quite a bit of time. There is also a company by Kurt Hazelton and Jack Baker, Risk something, that makes this software SP3 that attempts to do the same thing for a client. So an engineer could hire them to do it because of their experience, or the other way is interviews with the specific occupant of that structure. And I mean, this may be good or bad. We need to learn something new, but it may mean more billable hours for our companies and people, and perhaps give them more work. I don't know. But it is this problem is something that I don't think we can codify with a 0.8 times F prime C type of formula. It is much more complex.
Thank you. ¿Alguna otra pregunta? I have to, David de León from the University of Estado de Mexico says, how the input-output matrix of a region can be modified after a large event?
This is an excellent question because the answer is very carefully. So the input-output table approach has been developed by Leontiev. He is an economist originally from Russia, and basically the matrix is like a stiffness matrix for us. The column are the inputs to the economic sectors. Each row is an economic sector. Each column is an economic sector. It's the same vector. So if you are producing oil-based refined petrol, that goes into every other sector of the economy. But if you're producing, I don't know, textile, that only goes perhaps into one other sector or no. So this matrix gives you the connectivity of the sectors of the economy and also the flows in terms of money. It's a monetized flow of power, oil, textile, or whatever else goes in and out. The elements of the matrix, it is semi-diagonal and invertible and so on, some people try to change the elements of the matrix, these conversion numbers. Others affect the input vector, and as you reduce the input vector, for example, following one of those resilience curves, you could do a time sequence with the same I/O matrix and see how the outputs are affected. But I do not know which way is best, because I think both change, but there is some math that says that in that case the calculation is unstable and not guaranteed to converge. So I would be very careful in modifying things, and I would start with modifying the input and the output, knowing full well that the matrix should be changing also. But then if you touch that, then invertibility becomes questionable, and you may not have a solution.
I see. ¿Alguna otra pregunta? Preguntan if this presentation is going to be available.
I can give you a PDF.
All right, perfect.
And so where you post it,
we'll figure out.
We'll
And there are two people, one from Colombia and one from Uruguay, who are attending virtually and send regards. ¿Alguna otra pregunta? No hay preguntas, comentarios. Profesor, ¿no va a hacer usted una pregunta? No. Muy bien. Pues thank you very much. Boža me estaba recordando hace unos minutos que tiene guardado un diploma que le dimos cuando vino a dar una conferencia. Entonces yo le dije que dependiendo de su desempeño y qué tan resiliente fuera su trabajo, le daríamos otro diploma. So we have another diploma for you, for your lecture. So thank you very much. It's signed by our director.
Oh, thank you. Thank you.
And for you can take some souvenirs from our institute. So there's a cup of coffee and tea or what have you. And then we have a resilient instrument so that in case that your pen fails, you have a resilient
even better,
pen.
you captured carbon inside it.
That you're going to capture inside. That is true. So thank you very much.
Thank you.
And you can take these home.
Yeah, thanks.
Muchas gracias por haber venido. Thank you very much. You're always welcome to Mexico, as always. And
Thank you so much.
And you're your student, so thank you very much.
Thank you.
Gracias. Y tal vez los que son miembros de los capítulos, porque ahora se suben, yo no soy miembro del capítulo, pero si ustedes, se suben y se toman una fotografía con el profesor, si les parece bien. Diana, usted es miembro del capítulo. ¿Dónde está Ciprián? Acá está Ciprián. En fin, los que son capítulos, miembros de los capítulos. Take a picture of you with me. Member chapters, chapter members.